Among the many mysteries Cassini helped illuminate, one of the most perplexing remains Saturn's magnetic field. It doesn't just defy expectations, it outright challenges the very foundations of current scientific theory. Unlike Earth or Jupiter, Saturn's magnetic field is incredibly symmetrical. Its magnetic pole is almost perfectly aligned with its axis of rotation, to an accuracy of less than 0.1 degrees. According to the well-established dynamo theory, which explains planetary magnetic fields as generated by the movement of conducting fluids inside a planet, this alignment should be impossible. Yet Saturn doesn't just have a magnetic field, it has a powerful one. Cassini revealed that Saturn's magnetic moment is 580 times stronger than Earth's. This field plays a critical role in shaping the entire Saturn system. It protects the planet from solar wind, traps charged particles, and even influences its rings and moons. The true mystery lies in its origin. Scientists still don't know how this magnetic field is generated with such precision. Under known laws, a perfectly symmetrical magnetic field should decay, but Saturn's field remains stable and active. Cassini's detailed magnetometer readings didn't answer the puzzle, they deepened it. Furthermore, the magnetic environment of Saturn is complex and beautiful. The planet has a vast magnetosphere, an invisible shield of charged particles and magnetic forces stretching millions of kilometers into space. This zone acts as a kind of magnetic ecosystem, interacting with the solar wind and with Saturn's many moons, especially Enceladus, whose geysers spray water vapor and other molecules that become ionized and trapped in the magnetosphere. Auroras at Saturn's poles provide a visible sign of this interaction. Just like on Earth, charged particles spiraling along magnetic field lines crash into the upper atmosphere, creating dazzling curtains of ultraviolet light. Cassini captured these events in detail, showing how they changed with solar activity. Cassini also revealed how the rings themselves generate electrical currents when interacting with Saturn's magnetic field. These currents act like wires, connecting the rings to the planet's upper atmosphere. It's an electric universe in miniature. Charged dust, plasma flows, and magnetic storms all dancing in sync around Saturn. In many ways, Saturn's magnetism is a frontier of theoretical physics. It dares us to revise what we think we know about how planets work. Cassini didn't solve this mystery. It handed it to the next generation of explorers. At Infinity Beyond, we embrace the mysteries as much as the answers. For what is science, if not the constant adventure of discovering that the universe is more complicated and more wondrous than we ever imagined? Often overshadowed by its neighbors, Uranus is one of the most mysterious planets in our solar system. Though it may appear quiet and pale blue through a telescope, this ice giant harbors secrets that continue to intrigue scientists, especially when compared to its planetary sibling Neptune. Uranus has a mass of approximately 14.5 times that of Earth, slightly less than Neptune's 17 Earth masses. Yet its diameter is slightly larger, about 50,700 kilometers, roughly 4 times that of Earth. Because its mass is spread out over such a large volume, the surface gravity of Uranus is surprisingly gentle, clocking in at around 7.8 meters per second squared, or 0.89 times the gravity of Earth. Standing on a solid platform floating within Uranus's atmosphere would feel quite natural to us. It's one of the few planets where a human might feel relatively at home in terms of gravitational pull, though the rest of the environment is anything but welcoming. What lies beneath that aquamarine haze? Scientists believe Uranus has a small rocky core, roughly the size of Earth, made primarily of silicate and metallic elements. Surrounding it is a thick mantle of water, ammonia, and methane ices, hence the label ice giant. Above this is a gaseous envelope of hydrogen and helium. Despite its frigid distance from the Sun, Uranus radiates very little internal heat. In fact, it emits less heat than any other planet in the solar system. This lack of thermal energy makes its weather systems more subdued than Jupiter's or Saturn's, but not non-existent. Cassini did not visit Uranus, but data from the Voyager 2 flyby and later observations from Earth-based telescopes have revealed massive storms, atmospheric bands, and high-altitude haze layers. Another strange aspect of Uranus is its axial tilt. The planet rotates on its side, with an inclination of about 98 degrees. This means that its poles experience 42 years of continuous sunlight, followed by 42 years of darkness. Such extreme seasons have profound effects on its climate and atmospheric dynamics. In recent years, interest in Uranus has resurged. Scientists now suspect that its odd rotation and structure could be the result of a massive collision early in its history, possibly with an Earth-sized object. That event could have disrupted its core, altered its magnetic field, and tilted its axis dramatically. A future mission to Uranus, similar in ambition to Cassini's exploration of Saturn, could revolutionize our understanding. The data we have is limited, and the ice giant's distance makes missions challenging. But the scientific payoff could be enormous. Insights into planetary formation, atmospheric chemistry, and even magnetic field generation. At Infinity Beyond, we see Uranus not just as a planet, but as a puzzle, an invitation to look deeper, to ask more questions, and to prepare for the next great journey into the outer solar system. The final mission phase brought Cassini closer to Saturn than any spacecraft before. As it plunged past the planet during the grand finale, it was tasked with gathering some of the most detailed and unexpected data of the entire mission. It was as if, in its final act, Cassini chose to give everything it had left: fuel, memory, and courage. During these final orbits, the spacecraft created detailed maps of Saturn's gravity and magnetic fields. These weren't just charts for navigation, they were scientific blueprints, tools that would reveal the inner structure of this gas giant. Understanding Saturn from the inside is like trying to see the skeleton of a cloud, but Cassini's measurements brought us closer than we'd ever been to answering questions about what lies beneath its swirling bands. One of the most persistent mysteries Cassini sought to solve was the rate at which Saturn's interior rotates. Unlike a solid planet, gas giants don't spin uniformly. Their outer layers may move at different speeds than their core, making it difficult to calculate an exact day length. Cassini's readings provided essential clues: gravity variations, wave patterns in the rings, and magnetic field anomalies, all contributing to this complex puzzle. But Cassini didn't just look inward, it also looked around. It vastly improved our understanding of Saturn's rings. For decades, astronomers speculated about how massive these rings really are. Cassini's proximity allowed it to measure ring mass with remarkable precision. These readings hinted that the rings might be younger than once thought, possibly just 100 million years old, a blink in cosmic time. Through these observations, researchers could also study the composition and behavior of ring particles. Tiny collisions, density waves, and the interaction between moons and rings painted a dynamic, ever-changing portrait of Saturn's delicate system. This was not just a frozen relic of the past, it was a living, breathing disk of dust and ice sculpted by gravity and time. And while Saturn dominated the frame, its many moons never left Cassini's sight. The spacecraft flew close to icy Mimas, cratered Tethys, and mysterious Iapetus with its two-tone surface. Each world was like a different chapter in the story of Saturn's domain. Cassini's instruments continued to outperform expectations. In its final days, the spacecraft made ultraviolet observations of auroras dancing across Saturn's poles. It sniffed the atmosphere for organic molecules, and it watched as sunlight played across the planet's massive storm systems, each one larger than Earth. In many ways, these last orbits became a tribute to the scientists and engineers who dreamed the mission into existence, to the thousands of minds who spent years planning every detail, and to the spirit of exploration that drives humanity ever outward. At Infinity Beyond, we believe stories like these remind us that exploration is not about the destination. It's about the journey and the legacy we leave behind in the stars. Though our story has centered around Saturn, we cannot ignore its powerful neighbor, Jupiter. Together, these gas giants play a crucial role not just in shaping the outer solar system, but in protecting the inner planets, including Earth. Jupiter's gravity is so immense, it has acted as a cosmic vacuum, sweeping up asteroids and comets that might otherwise threaten the terrestrial planets. But it's not just a passive protector. Its gravitational influence actively shapes orbits, alters trajectories, and in some cases, prevents planets from forming at all. One notable example is the asteroid belt. Scientists believe Jupiter's immense gravity disrupted the formation of a full-sized planet between Mars and Jupiter. Instead, what remains is a vast belt of rocky debris, including objects like Vesta and Ceres, failed planets that never quite came together. Jupiter's reach extends even further. Its perturbations on Mercury's already eccentric orbit have led to predictions that, over billions of years, the tiny innermost planet could either crash into the Sun or be ejected from the solar system entirely. Gravity, in this case, isn't just a stabilizing force, it's a chaotic one. Saturn, though smaller than Jupiter, contributes significantly to this gravitational ballet. Together, they maintain a balance in the solar system that has allowed Earth to thrive. Without them, the bombardment of asteroids might have been far more frequent, and life, as we know it, might never have emerged. Cassini helped us better understand Saturn's gravitational role. Its orbits, meticulously calculated, allowed scientists to refine models of Saturn's mass, core structure, and orbital influence. With that data, they could more accurately simulate the interactions between planets over time. Interestingly, Saturn's own orbital resonances with Jupiter help stabilize the outer solar system. These two giants are not just companions, they are co-engineers of celestial harmony. Their gravitational interactions prevent many smaller bodies from destabilizing the planetary order. Cassini's data also helped scientists study near-Earth objects, asteroids that pass close to our planet, by understanding how planetary gravity affects their movement. While Saturn doesn't pull as strongly as Jupiter, its contribution to the overall gravitational dynamics is non-trivial. This protective role Saturn plays might seem distant, but it's deeply connected to our own existence. Our ability to evolve, to thrive, and to look outward with wonder is, in part, due to the silent vigilance of giants like Saturn. At Infinity Beyond, we remind ourselves that every world, large or small, has its role to play. Saturn is more than a ringed beauty. It's a guardian. And in its quiet orbit, it helps keep the solar system in balance. The dive, what it discovered before and during its plunge, and the incredible findings continuing to be unveiled to this day all trace back to the legacy of the Cassini-Huygens mission. If you want to witness Saturn's majestic beauty, there is no better lens than that of Cassini in its legendary grand finale. The journey began decades ago. The first probe to reach Saturn was Pioneer 11 in 1979. At the time, scientists made a groundbreaking confirmation. Triton, Saturn's largest moon, indeed had an atmosphere. That revelation alone was enough to convince the scientific community. Saturn needed another, deeper visit. Enter Cassini-Huygens. Launched in 1997 and arriving in the Saturnian system by 2004, it became a cornerstone of planetary exploration. Cassini didn't just pass by, it stayed, it studied, it revealed. Over the span of 13 years, Cassini orbited Saturn an astounding 293 times, gathering unprecedented data about its magnetic field, complex ring structures, and the multitude of its moons, some of which, like Enceladus, are now considered promising candidates in the search for extraterrestrial life. Its mission wasn't only a technical achievement, it became a poetic saga in the eyes of scientists and the public alike. And when it came time for its finale, engineers at NASA and ESO orchestrated a series of daring maneuvers. Rather than letting Cassini drift and crash into a potentially life-bearing moon, they sent it straight into the planet's atmosphere, ensuring a responsible end to its life, and one final opportunity to gather science. This decision, bold and beautiful, allowed the spacecraft to beam back valuable data during its descent. As Cassini dove between Saturn and its rings, it captured images and measured the composition of the upper atmosphere. These observations offered answers to questions that had lingered for decades. What is Saturn's rotation rate? How does its magnetic field work? Are there yet undiscovered rings or particles hidden within? The mission also advanced our understanding of the planet's seasonal changes. Saturn's years are long, almost 30 Earth years each, and Cassini was there long enough to witness significant shifts in temperature, color, and storm activity. This gave researchers on Earth a never-before-seen time-lapse of Saturn's evolving weather. Meanwhile, the Huygens lander, which separated from Cassini, made history of its own. It descended onto Triton, the only moon in the solar system known to have thick clouds, and a methane cycle similar to Earth's hydrological cycle. Huygens sent back breathtaking images of river channels, deltas, and what appeared to be ancient shorelines, suggesting the presence of methane lakes and seas. With over 4,000 scientific papers generated from its data, Cassini-Huygens didn't just study Saturn. It redefined how we understand giant planets. The ripple effects of this mission continue through every university lab, research institution, and science outreach channel, especially here at Infinity Beyond, where we're committed to sharing space's most awe-inspiring stories. Join us as we explore what Cassini taught us, not just about Saturn, but about the way we explore the cosmos itself. As Cassini approached the final leg of its journey, it continued to perform science with relentless determination. One of its most poignant final acts was a last glance toward Enceladus, the icy moon that had become one of the most tantalizing subjects of astrobiological interest in the solar system. For 40 minutes, Cassini watched as Enceladus slowly disappeared behind the vast, curving edge of Saturn. The image sequence it captured was haunting. The tiny white orb of Enceladus drifting away, while Saturn's body grew larger and darker in the frame, was symbolic of the mission's approaching end. The final photograph Cassini ever took wasn't a grand portrait. It was subtle, taken while peering over the region of Saturn where the spacecraft would ultimately plunge. It was nighttime on that part of the planet, and the only illumination came from sunlight reflected off the rings. It was, in every sense, a quiet farewell. But photography wasn't Cassini's priority on its last day. As beautiful as the images were, they consumed bandwidth, and the scientists wanted every bit of data they could get. The science team had made a decision: prioritize measurements over visuals. After all, there would be no more uploads once Cassini was gone. As it dove into Saturn's upper atmosphere, Cassini's instruments remained active to the very end. It measured temperature, pressure, magnetic fields, and the composition of the gases surrounding it. It sent data back in real time, knowing full well that it was the last communication it would ever transmit. Back on Earth, scientists watched in tense silence. In a control room at NASA's Jet Propulsion Laboratory, the signal was tracked with unwavering attention. Then, without drama or noise, it ended. A silent pause. The spacecraft was gone. Cassini's destruction wasn't a loss. It was a culmination. Its death ensured the protection of potentially habitable worlds like Enceladus and Titan, preventing any Earth-based microbes from contaminating them. It was a noble sacrifice in the name of future science. The images Cassini had sent throughout its mission remained, some of the most breathtaking views of space ever captured. Panoramas of Saturn's rings, shadows cast by moons, the pale blue dot of Earth seen from across the solar system. These weren't just photos. They were emotional artifacts of humanity's greatest robotic explorer. Cassini's final act was to look back one last time, not just at the moons it had studied, but at the legacy it was leaving behind. It had traveled nearly 5 billion miles, orbited Saturn for over a decade, and changed everything we knew about the ringed planet. At Infinity Beyond, we honor missions like Cassini not as endings, but as eternal beginnings, each byte of data it sent home now part of humanity's shared cosmic story. As we leave behind the gas and ice giants, one final marvel awaits us. The moons of Neptune, a diverse and mysterious collection of natural satellites, each telling a story of violent collisions, cosmic captures, and the outer reaches of planetary evolution. Neptune's moon system is unlike any other. Some moons, particularly the inner regular ones, orbit within or near Neptune's ring system. These moons, such as Naiad, Thalassa, and Despina, act as shepherds, maintaining the structure of the rings through gravitational influence. Their orbits are near-circular and equatorial, suggesting they formed with the planet. But further out lie the irregular moons, and these are where the story becomes stranger. Unlike the regular moons, these objects follow highly elliptical and often tilted or even retrograde orbits. Some move in the same direction as Neptune's rotation, prograde, while others move in the opposite direction, retrograde. These characteristics suggest that Neptune captured these moons long after the planet formed. They likely began life as independent objects, asteroids or Kuiper belt objects, that were pulled into Neptune's gravity well and trapped. Triton, Neptune's largest moon, is the crown jewel of this collection. It's the only large moon in the solar system with a retrograde orbit, and its surface is a wonderland of nitrogen ice, geysers, and frozen plains. Triton's orbit and composition suggest it was once a dwarf planet, possibly from the Kuiper belt, before being captured by Neptune's immense gravity. This capture would have been cataclysmic. Triton's arrival may have disrupted Neptune's original moon system, causing previous moons to crash into one another or be ejected entirely. What remains today is a restructured system, new moons, reshaped orbits, and gravitational scars. Then there are the true outliers. The outermost moons of Neptune, such as Neso and Psamathe, have orbits so large and slow that it takes them over 25 Earth years to complete a single revolution around Neptune. Their vast distances and loosely bound paths make them some of the most extreme natural satellites ever discovered. Neptune's moon system is a living museum of the solar system's chaotic past. Collisions, captures, and cosmic migration have left their marks on these icy bodies. Each crater tells of a journey, each orbit a memory of ancient events. While we await a dedicated mission to Neptune, perhaps one that could orbit for years and even land on Triton, our understanding remains based on brief flybys and distant glimpses. Yet what we know is enough to stir awe. And so we end our journey through the outer solar system, not with silence, but with the whisper of moons moving through the dark. Neptune's companions remind us that even at the edge of the sun's influence, the cosmos is never still. At Infinity Beyond, we believe every moon, every orbit, and every crater is part of the grand cosmic story. Thank you for exploring the giants with us. And stay tuned, because the universe always has more to reveal. When it comes to planetary weather, Neptune is a paradox. Despite being the most distant planet from the Sun, it hosts the most extreme atmospheric activity in the solar system. Winds reaching up to 2,100 kilometers per hour tear through its skies, faster than any hurricane on Earth, faster even than the speed of sound in some conditions. This begs the question, how can such a distant icy planet be so violent? Uranus, which is closer to the Sun, is actually colder than Neptune. That fact alone overturns assumptions that distance from the Sun strictly determines planetary temperature. In reality, Neptune has a secret. It radiates more than twice the amount of heat it receives from the Sun. This internal heat source is likely the key to Neptune's dynamic atmosphere. While the Sun plays a role in driving seasonal changes, something deep within Neptune is stirring the pot. Scientists believe that pressure within its icy mantle, composed of water, ammonia, and methane, creates friction and releases heat. This energy rises, fueling powerful convection currents that churn its upper layers. The result? Giant storms, massive jet streams, and turbulent cloud bands. The most famous of these is the Great Dark Spot, observed by Voyager 2 in 1989. This storm, roughly the size of Earth, was a swirling vortex of high-speed winds. Unlike Jupiter's Great Red Spot, however, Neptune's storm systems are transient. They appear and vanish over just a few years. Neptune's blue hue, while visually stunning, is not just for show. It's caused by the absorption of red light by methane in its upper atmosphere, while blue light is scattered outward. But that tranquil appearance masks a world of chaos beneath. The planet's magnetic field adds another layer of intrigue. Like Uranus, Neptune's field is sharply tilted and offset from its center. It too exhibits a corkscrew-like tail and undergoes rapid variation as the planet rotates. Such irregularities suggest a complex interior structure, perhaps a conducting shell rather than a central core, similar to the theories proposed for Uranus. Despite its distance and mystery, Neptune continues to fascinate astronomers. Telescopic observations from Earth have tracked changes in its weather patterns, storm development, and seasonal shifts. Yet a dedicated mission has yet to return since Voyager 2's historic flyby. Scientists are now calling for a Neptune orbiter, possibly with an atmospheric probe or lander. Such a mission would provide the kind of long-term data we saw with Cassini at Saturn. Until then, Neptune remains a cold frontier with a warm heart. At Infinity Beyond, we explore the extremes, worlds that defy expectations and force us to rethink the rules of nature. Neptune is a place where fire and ice coexist, where silence meets speed, and where mystery fuels our curiosity. While moons orbiting within the protective magnetospheres of gas giants like Jupiter and Saturn might seem shielded, the reality is far more dangerous. These environments are not safe havens. They are radiation realms of extraordinary intensity. Because they orbit deep within their parent planet's magnetosphere, many moons don't require their own magnetic protection. Instead, they are constantly bathed in the magnetic fields and plasma environments of the giants they orbit. This comes at a cost. Take Jupiter's moon Io, for instance. It passes through the most intense regions of Jupiter's radiation belts, zones packed with high-energy particles trapped by the magnetic field. Io's surface receives an estimated 3,600 rem, or Roentgen equivalent man, of radiation per day. For perspective, a dose of 500 rem is considered lethal to humans. Io would kill an unshielded human in minutes. Saturn's radiation environment is less extreme than Jupiter's, but still formidable. Cassini had to be specially designed with shielding to survive repeated passes through the magnetosphere. Even then, the spacecraft experienced degradation in its instruments over time, testament to the harshness of Saturn's space environment. Some of Saturn's moons, like Enceladus and Dione, are located in regions where radiation is less severe. However, charged particles still interact with their surfaces, creating effects that Cassini detected. For instance, icy surfaces become chemically altered as radiation breaks down molecules, possibly creating complex organics. Radiation isn't just a danger to machines or people, it's a geologic force. It alters atmospheres, carves surface features, and may even play a role in the creation of temporary atmospheres on moons that would otherwise have none. One surprising effect observed by Cassini was the interaction between Saturn's magnetosphere and its rings. As radiation particles spiral along field lines, they interact with icy ring particles, charging them and creating ring rain, a phenomenon where charged water molecules are funneled into Saturn's atmosphere. It's a strange, beautiful connection between magnetism, chemistry, and gravity. Understanding radiation environments is essential for future missions, especially those targeting habitability. For example, any spacecraft hoping to explore Europa, Io, or even Titan must be hardened against radiation damage. The lesson from Cassini and its predecessors is clear. Radiation is one of the most underestimated threats in the solar system. At Infinity Beyond, we explore not just the wonders, but the dangers of space. For in those challenges, we find humanity's next frontier, learning how to endure, adapt, and ultimately thrive in environments that were never meant for us. Among Cassini's most visually captivating discoveries were the tiny moonlets hidden within Saturn's rings. These miniature satellites, often no more than a couple of kilometers wide, were elusive to even the sharpest instruments on board. Some were barely visible, more like shadows or distortions within the ring material than discrete objects. Yet, despite their size, their impact was monumental. In the data Cassini sent back, scientists noticed something extraordinary. These moonlets were physically connected to the rings by bands of material, ribbons of dust and ice that stretched out behind them like cosmic trails. These interactions were not just beautiful, they were powerful. The moonlets were sculpting the rings themselves. One of the most fascinating regions Cassini observed was the so-called anchor gap, where a moonlet, perhaps no larger than a city block, had cleared out a space in the ring. It was a living laboratory of gravitational physics, where even the smallest object could shape the motion of countless particles. This wasn't an isolated event. Cassini identified multiple moonlets, all working quietly, carving gaps and creating ripples. Each had its own gravitational pull, enough to disturb nearby particles and form sharp-edged gaps and waves. The biggest of these moonlets, although still incredibly small by planetary standards, stood out as prime influencers of ring structure. None of these tiny moons were believed to have the density of a solid rock. Instead, they were likely rubble piles, loose collections of icy debris held together by gravity. Their fragility only added to their intrigue, making them some of the most delicate architects in the solar system. What Cassini gave us was not just photographs, but time-lapse evidence of the rings evolving. These changes didn't happen over millennia. They occurred over weeks and months. Watching Saturn's rings through Cassini was like watching a living system pulse and flow with every gravitational nudge. And this was the beauty of Cassini's close orbits. It allowed us to witness details never seen before. We saw ringlets inside ring gaps, braided patterns, spokes caused by electrostatic charges, and even seasonal changes in ring brightness. The closer we got, the more complex Saturn's ring system revealed itself to be. It wasn't just about icy particles and physics. These findings led scientists to ponder even deeper questions. Were Saturn's rings born from the remains of a shattered moon? Or are they younger than the dinosaurs, formed from some recent celestial catastrophe? The answers are still being debated, but Cassini brought us closer to understanding the rhythm of this ringed world. And every moonlet Cassini tracked was a note in that cosmic symphony. At Infinity Beyond, we celebrate the small wonders of the universe, The moonlets that teach us that size doesn't dictate importance, and that even the tiniest body can reshape the universe around it. After years of observation and fine-tuning, Cassini finally resolved one of Saturn's longest-standing enigmas, its rotation rate. Scientists determined it to be 10 hours, 33 minutes, and 38 seconds. While seemingly trivial, this measurement eluded precision for decades due to Saturn's unusual magnetism and atmospheric dynamics. But even with this puzzle solved, Saturn holds many more mysteries that call for a new generation of explorers. The next major chapter in Saturn exploration will unfold in 2027 when NASA launches the Dragonfly mission. But this time, the destination isn't Saturn itself. It's its largest and arguably most fascinating moon, Titan. Titan is, in many ways, the most Earth-like world we've found in the solar system. It has a dense atmosphere, rich in nitrogen, much like Earth's, but it also contains methane and ethane, creating an alien version of our own hydrological cycle. Instead of water, Titan rains hydrocarbons. Its lakes, seas, and rivers are filled with liquid methane. Cassini's flybys and the Huygens lander revealed incredible details. Titan has dunes, mountains, shorelines, and possibly even cryovolcanoes that spew icy material instead of molten rock. Its thick, orange-hued atmosphere shields the surface from direct observation. But radar and infrared instruments peeled back the curtain. With all of this potential, Titan became a prime target for astrobiology. Could life evolve in liquid methane? Are there subsurface oceans of water beneath Titan's icy crust? Cassini raised these questions, but only future missions like Dragonfly can seek the answers. Dragonfly is no ordinary lander. It's a rotorcraft, a flying laboratory capable of hopping from one region of Titan to another. Unlike traditional rovers that crawl across terrain, Dragonfly will soar above dunes, craters, and riverbeds. Its design gives it unparalleled mobility, allowing it to explore a wide range of environments. Its mission is ambitious. Analyze the chemical makeup of Titan's surface, search for signs of prebiotic chemistry, and study how an atmosphere so thick could evolve on a moon so cold. Though Cassini is gone, its legacy guides Dragonfly. Every image, every radar scan, every spectral reading helped scientists choose the perfect landing site. Titan was once a mysterious dot in the sky. Now, thanks to Cassini and the upcoming work of Dragonfly, it's a dynamic world on the edge of becoming familiar. At Infinity Beyond, we see Titan not just as a moon, but as a mirror to ancient Earth, and perhaps a preview of worlds waiting beyond. Cassini gave us the map. Dragonfly will write the next chapter. Much of Uranus's complexity is invisible to the naked eye, hidden beneath layers of haze and distance. But with advances in infrared telescope technology, scientists have begun to peel back the curtain, revealing a world more active and mysterious than once imagined. Many of Uranus's atmospheric features, including storms and cloud bands, are now believed to be caused by seasonal changes. Though its distance from the Sun means seasons are slow, each lasting over 20 Earth years, their impact is immense. As one hemisphere is plunged into darkness and the other into prolonged daylight, thermal imbalances stir deep atmospheric currents. Infrared imaging has been especially revealing. Unlike visible light, infrared can penetrate Uranus's upper haze layers, allowing astronomers to observe banded structures, faint stripes that encircle the planet much like those seen on Jupiter or Saturn. But these bands are subtle, only visible in specific wavelengths, which explains why Voyager 2's cameras didn't capture them clearly in 1986. Even more intriguing are the small, scattered storms that dot Uranus's upper atmosphere. These appear as bright spots in infrared, often short-lived and moving rapidly. Though less dramatic than Jupiter's Great Red Spot, Their presence hints at dynamic processes still unfolding in this frozen world. Another standout feature is Uranus's magnetosphere, one of the most unusual in the solar system. Typically, a planet's magnetic field originates near its geometric center, aligned somewhat with its axis of rotation. Not so with Uranus. Its magnetic field is wildly tilted, nearly 60 degrees off-axis, and offset far from the planet's center. This asymmetry creates a lopsided, wobbling magnetic environment that changes dramatically as Uranus rotates. The magnetotail, instead of trailing neatly behind the planet, twists into a corkscrew shape through space. Voyager 2 detected this anomaly during its brief flyby, and Earth-based studies have since confirmed its strange configuration. The origin of this magnetosphere is still debated. One theory suggests that the conducting material responsible for generating the field lies in a shell of ionic fluid, rather than a traditional metallic core. This would explain the odd orientation, but it also raises new questions about how such a system formed and persists. Uranus continues to challenge our expectations. Beneath its serene appearance lies a world shaped by extreme seasons, tilted forces, and hidden storms. It reminds us that appearances can be deceiving, especially in the realm of planetary science. At Infinity Beyond, we're committed to uncovering what lies beneath the surface, not just literally, but conceptually. Uranus teaches us that even in the cold and quiet corners of the solar system, there is motion, complexity, and discovery waiting just beyond the visible light.